Good evening, guys. So let's get started. So yesterday we started the dual nature of radiation and matter, and we completed till the effects that were there, right? So let's just recollect those points alone. So yesterday we saw this Hall watch experiment. After this Hall watch experiment, we understood how the effect of intensity of incident radiation would affect the photoelectric current. Then how is the effect of potential difference affect the photoelectric, potential difference affect the photoelectric current, in which we kept the intensity and frequency constant and then we performed the experiment. And the next is, we saw how the effect of frequency of incident radiation would affect the stopping potential. Right. So today we are going to see the laws that are involved in photoelectric emission. So if you observe, the experimental observations of photoelectric effect may be summarized as follows, which are known as the fundamental laws of photoelectric emission. The same thing is again stated under Einstein's theory of photoelectric effect also. So if you take a given photosensitive material, right, like how that C and A were there. If you take a given photosensitive material, there is a minimum frequency called as the threshold frequency, below which emission of photoelectrons will completely stop, however great the intensity may be. This is proposed like a theory. So what they're trying to say is, you need to definitely ensure that the incident is having the minimum frequency called as a threshold frequency for you to observe this kind of a phenomenon, whatever it is, the light that is falling. Secondly, for a given photosensitive material, I repeat, for a given photosensitive material, the photoelectric current is observed to be directly proportional to the intensity of the incident radiation, provided the frequency is greater than the threshold frequency. Okay. So if you're able to overcome the threshold frequency, then you can observe that the photoelectric current is directly proportional to the intensity of the incident radiation. Next, it is important that photoelectron is an instantaneous process. That is, as soon as light falls on the surface, the electrons are, if it is crossing the threshold frequency, the electrons are said to get ejected out. So there is absolutely no time gap that is existing between the incidence of radiation and the emission of photoelectrons. Okay. And the fourth point is, the maximum kinetic energy of the photoelectron is directly proportional to the frequency of the incident radiation, but is independent of its intensity. This also we saw yesterday. So the maximum kinetic energy will decide the stopping potential. And when you keep the intensity constant, okay, when you keep the intensity of the radiation constant, then it is observed that the stopping potential is the same for all the materials. Right. Suppose what we did in this experiment, we did no. Even if you try to increase the intensity by keeping the frequency constant, the stopping potential came out to be the same value. Whereas when you increase the frequency, keeping the intensity constant, it was observed that the stopping potential also increased. Right. When that is going to be the scenario, this is the point we are going to state. That is the maximum kinetic energy of the photoelectrons is directly proportional to the frequency of incident radiation, but is independent of its intensity. Okay. Are these points clear?
Yes, that's clear.
So these are all the these are all the conclusions that we have drawn from the experimental observations. Now, we will discuss about light waves and photons. So, the electromagnetic theory of light was proposed by Maxwell, which could not explain the photoelectric effect. So, when I say electromagnetic theory, I'm talking about the wave nature. But Max Planck's quantum theory successfully explains photoelectric effect. So, according to Planck's quantum theory, light is emitted in the form of discrete packets of energy, which is called as quanta or photon. Quanta is plural of quantum. So, what did he say? According to the Planck's quantum theory, light is emitted in the form of discrete packets of energy, which is called as quanta or photon, and the energy of each photon is equal to h into nu, where h is called as the Planck's constant. Okay, so it can be understood that if you take a photon is neither a particle nor a wave. In the phenomena like interference, diffraction, polarization, the photon behaves like a wave. In phenomena like emission, absorption, and interaction with matter, photoelectric effect, that is, photon behaves like a particle. Hence, the light photon is said to have a dual nature associated with it. So, this is what I told you in the beginning of the chapter itself. This one we saw in the previous chapter also. So, we need to understand that what light is taken into consideration, light is studied under the phenomenon of interference, diffraction, and polarization. Light is considered like a wave. Whereas the same light, when it is dealt under the concept of emission, absorption, and interaction with matter, then light is considered like a particle. Hence, light is said to have dual nature. Okay. Based on this, we are going to see the next important topic, that is Einstein's photoelectric equation. So in 1905, what happened? Albert Einstein successfully applied the quantum theory of radiation to photoelectric effect. So according to Einstein, the emission of photoelectron is the result of interaction between a single photon of the incident radiation and an electron in the metal. Means if you take, so Max already told that light will start traveling in small packets of energy, and that small packets of energy was what is called as quanta or photon. Here what is happening, when light interacting with an electron, so a single photon will interact with an electron in the metal. So when the photon is of energy h nu is incident on the metal surface, its energy gets used up in two ways, which I already told you yesterday itself. So the energy according to Planck's equation is h nu. So this h nu needs to do two things. What is it? A part of the energy of the photon, that is part of h nu, is used in extracting the electron from the surface of the metal, since the electrons in the metal are bound to the nucleus. And this energy W spent in releasing the photoelectron is known as photoelectric work function of the metal. So how do you define work function? So the work function of a photometal is defined as the minimum amount of energy required to liberate an electron from the metal surface. This is what we need to understand. Okay. Okay. Now the question is, part of it is used to overcome the work function. What about the remaining part? So the remaining part of the energy of the photon is used to impart kinetic energy to the liberated electron. If m is the mass of the electron and p is the velocity, then the energy of the incident photon is taken as work function plus kinetic energy. So h nu will be equal to w naught plus half mv square. So this is what is called as the Einstein's photoelectric equation, right? So if the electron does not lose energy by internal collision as it escapes from the metal, the entire energy h nu minus w will be exhibited as the kinetic energy of the electron. So what they're trying to say is, during the process, the electron is trying to come out of the atom. If it is not undergoing any collision with the internal structure of the atom, then this value h nu minus w naught will get completely converted into kinetic energy. Then this h nu minus w naught represents the maximum kinetic energy of the ejected photoelectron. Similarly, if I take Vmax is the maximum kinetic energy with which the photoelectron is emitted, then the first equation can be modified as h nu is equal to W plus half m into Vmax square, and this equation is what is called as the Einstein's photoelectric equation. Okay. Now, this frequency is there, right? When the frequency of the incident radiation is equal to the threshold frequency of the metal surface, then the kinetic energy of the electron is zero. At that point, what will happen? H into nu naught will be equal to work function. So that is why we say work function is equal to H into nu naught. So I hope you guys are writing along with me. So what was stated? H nu is equal to W plus half m Vmax square. So h nu is equal to h nu naught plus half m into Vmax square. So h into nu minus nu naught is equal to half into Vmax square. At this point, what will happen is, if nu is equal to nu naught implies kinetic energy is zero, right? When kinetic energy is zero, it implies h nu is equal to h nu naught, and in this case, h nu naught is what is called as the work function. You can either write it as W or W naught. Okay. So h nu is equal to h nu naught plus half Vmax square. When you substitute all these things, right, then we get an option to draw the graphs between the kinetic energy and the frequency. Okay, h nu minus h nu naught is equal to half m into Vmax square. So if I take half m into Vmax square on the y-axis, h nu on the x-axis, plus c. So it starts something like this. Where this point will be called as the work function W naught. So because it is of the form y is equal to mx plus c. Or I can take it like this also. If I take only frequency also, it will be something like this. Then the slope of this line will be h. Okay. Now, the experimental verification of Einstein's photoelectric equation. So according to Einstein's photoelectric equation, h into nu minus u naught is equal to half m Vmax square. If you say V naught is the stopping potential and E is the charge of the electron, then we know the fact that half m Vmax square is equal to E into V naught. So from this, I can conclude that h nu minus h nu naught is equal to E into V naught. So what will be the value of V naught? V naught will be equal to h pi E into nu minus h pi E into nu naught. So if I take V naught on y-axis, this will be of the form y is equal to mx plus c, and this equation represents a straight line. So if I take V naught on y-axis, nu on x-axis, then it will be something like this. Then this distance is h nu naught divided by E, and this point will be nu naught, right? And the slope of this line will be h divided by E. I hope you remember from yesterday's discussion. I already told this point. If you see again and again, you need to concentrate more on graphs to make this chapter. Is it clear, guys? Yes or no?
Yes, sir.
So the next concept that we need to discuss is matter waves. This is the last part of the chapter. And with this, we are done. Okay. Matter waves and wave mechanical concept of atom. With that, we are done. So the radiant energy has dual aspect. Radiant energy means light. Dual aspects of particle and wave. Hence, a natural question arises, that is whether the symmetrical pattern is applicable or not. If radiation has dual nature, why not matter? The reverse question was asked. So in 1924, what happened? A French physicist, Louis Debroise, put forward the bold hypothesis that moving particles should possess wave-like properties under suitable conditions. So what did he say? He told that moving particles should possess waves. So when waves can possess particle nature, particles would possess wave nature. So he reasoned this idea from the fact that nature is symmetrical and hence the basic physical entities, matter and energy, should have symmetrical characters. Okay. So if radiation shows dual aspects, so should matter. That is what they're trying to say. Now the next question is Debroise wavelength of matter waves. So what did he do is, he equated the energy equations of Planck and Einstein. So what is the energy equation according to Planck? For a wave of frequency nu, the energy associated with each photon is given as E is equal to h nu. Let me call this as equation number 1, where h is Planck's constant. Then according to Einstein's mass energy relation, a mass is equivalent to energy. So E is equal to mc square. Let this be 2. Right. Now, if I equate these two, then what do I get? I get h nu is equal to mc square. But nu is c divided by lambda. This is equal to mc square. So c and c will get cancelled. Lambda is equal to h divided by m into c. But h divided by mass into speed is what is called as linear momentum. I'm sure this formula you would have seen. This is called as Debroise wavelength. So lambda is equal to h divided by mv. Did you guys see this in chemistry or not? So lambda is equal to h divided by m into v. Okay. Now, this is the Debroise wavelength of matter waves. It is generally written for any matters. If I have to specifically write it for an electron, if I have to write it for an electron, then what is going to happen? When an electron of mass m and charge E is accelerated through a potential difference V, then the energy EV is equal to the kinetic energy of the electron. Then I can write half mv square is equal to E into capital V. Then V will be equal to square root of 2 into E into capital V divided by m. Right? But we know that lambda is equal to h divided by m into V. So this will be h divided by m into V is square root of 2e into V divided by m. So this will give us h divided by root of 2m into E into V. Right. Now if you substitute all the known values from the equation, that is the value of H, M and E, you will get lambda is equal to 12.27 divided by square root of V times square root V angstrom.
So I have a doubt, sir.
Tell me.
Sir, there are two V's in this equation, right, sir? At the start.
2 V, sir.
Yes, sir, but one is half mv squares and the other is ev. Right?
This is velocity. This V stands for potential difference. It is basically work energy theorem. The work done by electrostatic force is getting converted to is equal to change in kinetic energy. That's the meaning.
So energy is conserved here, sir.
Yes. Provided the internal collisions are ignored. That's what I told you, right, at the beginning. So read the statement carefully. So if you have an electron of mass m and charge E, and you put that electron through a potential difference V. So I have a potential difference V through which I'm putting this electron. Then what is going to happen? EV will be the work done by the electrostatic energy. This EV is what is creating the kinetic energy, half mv square. That is what we are trying to say. Because for any
potential difference is stopping potential, sir.
No. Here we have no. See, you are getting confused between two things. See, stopping potential is a concept which is used only in the case of photoelectric effect. But is the concept here related to photoelectric effect?
Yes.
No, because it is Debroise wavelength of an electron. So what we are trying to calculate is, try to understand. I'll repeat it again. See, there is an electron which is at rest. Okay.
Okay, sir.
And displaced in the direction of opposite force. Can I say work is done? Can I say work is done?
Yes, displayed work is done.
And okay, now I'll take this electron and put it in a chamber of small potential difference. Then what will happen? The electron tends to accelerate.
Yes.
So E into V will be the amount of work done by the potential difference. Because
okay.
So this work the difference is half. So this difference that you're applying here need not be a stopping potential, because here I have to photoelectric effect. I only have an electron in my hand. I already have an electron. In photoelectric effect, what is happening? We are emitting an electron by applying light. So both are different contexts. Okay. So what I'm trying to say here is, try to understand. Means you need to understand what are matter waves. So with the photoelectric effect condition, that is the combination of 10th and 11th chapters first part put together, we understood that light had dual nature. Correct? So light is what? Light is wave. When wave can have a particle nature, the immediate symmetrical question that got raised was, why not a particle have a wave nature associated? Means what I'm trying to say is, electrons, we know that according to Bohr's theory, we know that electrons revolve in a circular orbit, but electrons are not only going to be in circular orbit, they are also going to have a wavy motion associated like this. And these waves that are generated due to this matter is what is called as matter waves. Are you able to understand?
Yes, sir.
That is the meaning. So for those matter waves, so matter means generally matter is something which has only mass and occupies some space. That is what chemistry definition says. But here we are combining two terms, matter as waves. So when I use the word waves, means I'm saying a particle has wave nature associated with it. Waves generally have a wavelength associated with it. And for those particle waves, the wavelength formula was given by Debroise. So what did he say? He told that lambda is equal to h divided by mv. Did you understand this derivation?
Yes, sir. That's understood.
Here what did he say is E is equal to h nu is Planck's equation according to wave theory. E is equal to mc square is Einstein's energy equation according to matter theory. According to particles.
Yes.
So he equated wave nature and particle nature. Then he came to a conclusion of an expression that is lambda is equal to h divided by m into v. This expression I'm sure you would have seen in chemistry. If not, also not a big deal. Now you have learned it. So lambda is equal to h divided by mv. Correct? Now what we are doing is this h divided by mv is a specific equation for a matter wave. That matter can either be an electron, proton, or whatever it is, provided it has some charge. Okay. Now the next question is, if I want to derive the same Debroise wavelength for an electron, I'm electron specific in this case. Then what I'm trying to do is, I'm taking that electron and putting it in a chamber where there is a potential difference of V existing, and the work done by that potential difference is directly appearing as kinetic energy. We know that energy gets converted from one form to another. So the electrostatic potential energy is directly appearing as kinetic energy. Is that clear?
Yes, sir. It's clear.
Now is the confusion gone from your mind? This V is not stopping potential?
Yes, sir. It's gone, sir.
Yes, that's gone, right? That is important. So E into V is equal to half mv square. This V is the potential difference. So we know that lambda is equal to h divided by m into V. Right? So h divided by, can I write this as m into, in the place of V, can I write it as square root of 2 into E into capital V divided by m? Then lambda will be equal to h divided by square root of 2m into E into V. Understood?
Yes, sir.
So what you are going to do is, you will substitute the value of h, m, and E, and you will get the value as 12.27 divided by square root of V, where the V is potential difference, angstrom. So this value you can remember. Sometimes what they will do is, in exam they will give you the potential difference and ask you to calculate the Debroise wavelength of an electron. So what you should do, 12.27 divided by whatever potential they give, put it there, those many angstrom. Remember the unit, it is in terms of angstrom. Okay. Shall I proceed?
Yes.
So the last concept of this chapter is wave mechanical concept of an atom. So according to Debroise hypothesis, we are clear that an electron of mass m in motion with a velocity v is associated with a wave whose wavelength is lambda, and that lambda is h divided by m into v. Right. So on the basis of Debroise hypothesis, an atom model was proposed in which the stationary orbits of Bohr model were retained. So what happened? I'm not sure if you remember what is Bohr's theory. So Bohr stated that electrons cannot revolve around the circular orbits. Electrons cannot revolve in some random circular orbits. Rather, electrons will revolve in those orbits in which the angular momentum is quantized. I'm not sure if you guys have heard of this. This is there in chemistry also. So he mentioned that MVR should be equal to NH by 2 pi. MVR is angular momentum. N into H by 2 pi is a condition for quantization. This is called as Bohr's quantization condition. So what happened is this theory could support it. So stationary orbits of Bohr's model were retained, but with the difference that electron in various orbits behaves as a wave. This is shown in the figure. See, for example, you take the 6th Bohr orbit. I told you, right? Electrons will not only revolve around the circular orbit, they will also have a wavy structure around them. So it is suggested that stationary orbits are those orbits in which the orbital circumference. So if I take the radius of that orbit as r, then the orbital circumference is going to be 2 pi r. The circumference of that orbit is 2 pi r. So this 2 pi r should be an integral multiple of wavelength. Means if an electron starting here, see, observe, This is one wave, right? This is second wave. This is third wave. Like this, if the electron has to come back to the point where it has started, it should be able to complete in such wavelengths. Okay, so that is why what we are trying to say is the distance from here till here, if I call it as one wavelength, then n such wavelengths put together will be equal to 2 pi r. That n can even be 1 also, we don't know. So 2 pi r is equal to n lambda. Now what is going to happen is 2 pi r will be equal to n into, according to Debroise, what is the value of lambda? It is h divided by m into v. Take that mv to the other side. So mvr is equal to nh divided by 2 pi. So this mvr is what is called as angular momentum, and the angular momentum is said to be quantized. Is that clear, guys? Is that clear? And this is what is called as Bohr's postulate. Did you understand what I meant in this? So this is a very simple derivation. What did we do? We know that orbital circumference should be equal to n times lambda. So 2 pi r should be equal to n into lambda is h divided by mv. And you take mv to the other side, mvr is equal to nh divided by 2 pi. Right? To nh divided by 2 pi. Right. So the last page contains the summary. So what I will do, I will share these notes with you guys, and you can go through the concepts again. So read the concepts from here and have the recording as reference to see if you have any doubts. Is it clear? So that is all with respect to this chapter from my side. So I don't want to dump everything on a single day. As I told you, all these chapters are very small. Atoms will take 2 more days. Nuclei will take 2 more days, and semiconductors will take 2 more days. So maximum 6 more classes we are done with. We're done with physics actually. Okay. So after this, what I will do, whatever doubts you have, I'll start solving some assignment and important question based on your preparation level. We can have a discussion. Okay, I don't want to actually start the next chapter. If I start, I can complete it tomorrow itself. But I'm giving you some breathing space to go through these concepts. Just revise them and come. In tomorrow's class, I'll start atoms chapter. Okay.
So I have a doubt.
Please tell me.
We had Davison and Germer experiments.
You don't have that. 1 minute. I think it has removed 1 minute. It has not been there since last year. Is this chapter taught in your school?
Yes, sir. Today it got over.
Today they started?
No, it got over today, sir.
Oh, today it got over. No, it's not there.
So deleted.
I'll read out the portions. Listen to this. Okay, I need to read out. I'll better share it here. See. So dual nature of radiation, we completed photoelectric effect, Hertz and Leonard's observation, Einstein's photoelectric equation, and particle nature of light. Experimental study of photoelectric effect is the one where we discuss those 3 graphs, no? Intensity, potential difference, and all those things. Matter waves and wave nature of particles and Debroise relation. That's it.
Okay, sir.
Okay. So this chapter, if you see, the next one is even more small. And this one is also small if you look at the number of subtopics.
Yes, sir.
Okay. Yeah. So don't worry about these things. The chapters which you need to concentrate more upon is 9th and 10th. Those are the toughest chapters. Concentrate upon them. Okay. So that's it, guys. We can wind up.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.